is October 2024 paper. Question number 16. An ester X with the molecular formula C8 H16O2 has the structure shown. Okay. Deduce the name of the alcohol used to synthesize X in a reaction with ethanol chloride. So ester can be prepared by the reaction of alcohol with ethanol chloride. So they are asking to deduce the name of the alcohol, like from which alcohol this is like produced. So of course, this part would be an alcohol, isn't it? This part would be an alcohol, right? So this would be your alcohol. So then what should be the name of this alcohol? What do you think? Mhm. So it would be,
It's going to be 3-methyl pentan 3-O.
let me select the longest carbon. This is the longest carbon in which you can see 1, 2, 3, 4, 5. So it's gonna be 3-methyl. It has only one branch, 3-methyl. In the long chain, it has 5 carbons. It's gonna be pentane. It's gonna be pentane, and the OH would be present at the third position. Yeah. So it's gonna be 3-all. So 3-methyl pentane 3-all. One of the proton environments in X is labeled A. Okay. Complete the labeling of this structure to show each of the other proton environments in X, clearly linking any that are the same. So, um, yes. So, what are the other proton environments that I'm supposed to select? So, this would be the
There's
different
gonna be one
environment.
on the first. Yeah, C. Yeah, and then there is the
Yeah.
ones that is like the H2C above the C.
Like this CH2 and this CH2 would be the same,
Yeah,
isn't it?
yeah,
And then
yeah. And
this
then the
CH3
last one is the
and this
CH2
CH3 would be the
beside
same.
it. Yeah, yeah,
So it's gonna be B. This is going to be B. This is going to be C, and this is going to be D. To total, we have 5 environments: A, B, C, D. No, 4 environments in total. Describe 3 ways in which the high resolution proton NMR spectrum can be used to distinguish between the methyl groups in X other than A. Yes. So basically, this is the methyl group, which is attached with the C double bond O group, right?
yeah.
And then I have CH3, CH2. This is also methyl group, which is attached with the CH2 group. And also, they are saying it's a high resolution proton NMR spectrum. High resolution proton NMR spectrum. So of course, high resolution NMR spectrum means that we have to see the neighbor as well, because we have to apply n+1 rule. Let's say n+1 rule means that if I ask for the high resolution NMR spectrum, the neighbor of this CH3 is this CH2. So it's mean that it's gonna be triplet. It's gonna be triplet. Also, it would be giving us triplet. And by the way, they have the same chemical environments. And if you can see this CH3, and if you can see this CH3, so the neighbor of this CH3 is this carbon having no hydrogens. Having no hydrogen. So it would be giving us singlet, isn't it? Yes or no? Also, it
Yeah.
would be giving us singlet. Why? Because there is no neighbor, there is no any hydrogen in the neighbor, right? So it's of 3 marks. So first of all, I'm supposed to write that uh, chemical shift. If you can see the data booklet, chemical shift for CH3C double bond O. I'm talking about this one. CH3C double bond O will be at 1.6 to zero point 0 ppm. Because you know what they are saying? Three ways in which the high resolution NMR spectrum can be used to distinguish between the methyl groups in X other than A. Other than A, right? So, okay. So it would be present at 1.6 to 3.0 ppm because it gives us a singlet, right? It gives us a singlet. That's why. And also, I would say that and at high resolution NMR and at high resolution NMR, there would be there would be singlet for CH3CO as as there is no hydrogen, as there is no hydrogen on adjacent carbon. There is no hydrogen on adjacent carbon. First of all, this thing. And and for CH3CH2, for CH3 and then CH2 group, there will be there will be triplet. There will be triplet as there are two hydrogens, as there are two adjacent hydrogen. Okay. So in this way, I can say we can distinguish between the methyl groups. And also, um, what would be the peak area? What would be the peak area, relative area, of course. So as we know that there are two CH3s and this is only one. So the relative area for the methyl groups which are attached to this CH2 group, it would be having the relative area as twice as this one because they have six hydrogen atoms and it has only three. So yeah, this is also the other way to distinguish between these two methyl groups. Yeah, so I can say that. So I can say that uh, relative peak area, relative peak area for CH3 groups attached with CH2 attached with CH2 will be twice will be twice the area as compared to CH3. C double bond O. In this way, we can distinguish, by the way. Are you getting my point?
Yeah.
Okay, because due to six hydrogen atoms, and this is the three hydrogen atoms, that's why. So 6 into 3. So the ratio is 2 is to 1. That's why I'm saying. The area is twice. An isomer of X is a carboxylic acid with 5 peaks in its carbon 13 NMR spectrum. Draw a possible skeletal structure for this carboxylic acid. An isomer of X. This is your X. This is your X. An isomer of X, and by the way, this is ester. This is ester. An isomer of X is a carboxylic acid with the 5 carbon atoms. Okay. Draw a possible skeletal structure for this carboxylic acid. It must have a 5 peaks. Remember, it must have a 5 peaks. So let me count the total number of carbon atoms in that structure, as they have told us that they are supposed to have 8 carbon atoms. 8 carbon atoms. Okay. So I have to draw the structure containing 8 carbon atoms in such a way that this is supposed to be carboxylic acid and it must have a 5 peaks in its NMR spectrum. So I would say that uh, carboxylic acid. Okay. Hmm. What if I'm going to draw this 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. Then this is going to be, and this is going to be carboxylic acid. Let me count the total number of atoms. So this is going to be CH3. This is 2. This is 2. CH2. 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 And this is going to be H. So 3 plus 2 plus 2 plus 2 plus 2 plus 2 plus 2 plus 1. So are you getting the same number of hydrogen atoms as they have quoted? That is 16. Yeah, we have two oxygen atoms and hydrogen should be 16. So 5, 7, 9, 11, 13, 14, 15, 16. Yes. So the formula is perfect. Now we have to see how many environments it has. So 1, 2, 3, 4, 5, 6, 7, 8. Oh my God, eight chemical environments. No, they are saying it's supposed to have five chemical environments. So yes, what should I draw the structure to make the five chemical environments in total? Else I can try this one as well.
Like we can do like seven, we can do seven carbons, so like the zigzag. And on the fourth carbon we could have like a methyl group with the with a double bond to oxygen and um the OH.
Like you're saying this one, skeletal they are saying, right? So I can say this one.
Yeah.
So 1 and 1, 2 and 2, 3 and 3. Three environments. This is going to be 4 and this would be 5. Yeah, this is perfect. This is perfect. It has a 5 chemical environments in total. And also we can check that the molecular formula is same. Yes, molecular formula is the same. Say 8 carbon atoms, it has 16 hydrogens, and there are 2 oxygen atoms. Yeah, that's perfect. Okay. The painkiller aspirin is also an ester. Oh, okay. Formed by the reaction of 2-hydroxy benzoic acid and ethanoic anhydride. Okay. So for this one, part of the mechanism for this reaction is shown. Part of this reaction for this reaction is shown. Okay. Okay. So add a single curly arrow to step 1 and a single curly arrow to step 2. To complete this part of the mechanism, state the role of the H positive ion in the synthesis of aspirin. First of all, we have to draw the curly arrow. So what do you think where I'm supposed to draw the curly arrow? Of course, curly arrow means that always remember, always like the
It's going to,
arrow would be pointing out from the
yeah,
electron.
it's,
That's the
yeah,
concept.
it's for the step one, it's going to be from the lone pair of electrons on oxygen to the
Like
H
that.
plus.
Like that.
Yeah. And
Okay.
one second. Yeah,
Okay. And then in
and
the
and
second
in the
one,
sec and in the second one, it's gonna go from the lone pair of electrons on oxygen to the C, which is with the OH plus.
exactly. It has a positive, right? Okay, good. And then state the role of the H positive ion in the synthesis of aspirin. Role of the H positive ion. Yes. It seems like that it's acting as an acid, but the thing is that acid is a proton donor. But right now over there, it's not acting as a proton, I think so. Like it's not acting as an acid. So I would say that uh, it would be acting as a catalyst. It would be acting as a catalyst, right? It would be acting as a catalyst. So yeah, so the role of H positive ion in the synthesis of aspirin is to act as a catalyst. Is to act as a catalyst. Yes. So 6 marks. Okay. This question is about acids containing sulfur. Sulfuric acid reacts with sodium hydroxide solution as shown. Calculate the pH of the solution formed when 20 centimeter cube of sulfuric acid of concentration. This one is mixed with this one concentration. This one. Give your answer to one say decimal place. Kw is given to you. That is 1 exponent minus 14 mole square dm minus 6. So it's a buffer solution. Yeah. No. Okay. So buffer solution, no, it's not a buffer. Yeah, so we have to find out the pH of the solution formed. So what do you think, which concentration I am supposed to take, right, to calculate the pH, because the formula for the pH is equal to negative log of H positive ion. Negative log of H positive ion. Try yourself. I'm going to give you few moments, then I'm going to solve it. Just try. Mhm, 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 mhm. I'm also doing, you can match with your calculation. So, first of all, I am going to find out the moles of sulfuric acid. Okay, so mole of H2SO4, mole of H2SO4 is equal to 20 multiplied by 10 raised to the power minus 3. I'm going to convert it into a decimeter cube, and the concentration is going to be 0.0720. So the number of moles of sulfuric acid is gonna be 1.44 into 10 raised to the power minus 3 mole. This is the mole for sulfuric acid. Then I'm going to find out the moles of sodium hydroxide, right? So mole of NaOH, mole of NaOH is equal to the volume. I'm going to convert it into the decimeter cube multiplied by the concentration. That is going to be 0.240. So the answer would be uh, 0.0192 mole, right? So, and also, then after doing this, then after doing this, what I am supposed to do for this one, yes, have you found the moles?
Are you asking the moles of uh
Moles of both.
both, like as in the hydroxide or like the hydrogen and sulfuric?
Yeah, hydroxide, sulfuric acid
Um,
as well.
hyd hydroxide is gonna be 0.0192.
0.0192.
Zero,
Okay.
yeah.
So then
And
what you did,
for sulfuric, it's gonna be 1.44 times 10 to the power of minus 3.
okay, then
Yeah. Um, then I just subtracted
subtract it from what?
because I calculated the moles of hydrogen, so I subtracted the moles of hydrogen from the moles of hydroxide ions.
So what did you get after the subtraction?
0.01632 moles.
Okay, so okay, moles of H positive ions, because 1 mole of sulfuric acid can give us 2 moles of H positive ions. This is very important to know, right? 1 mole of H2SO4, this is very important. 1 mole of H2SO4 gives 2 H positive ions, isn't it? So if I'm going to find out the mole of H positive ions, so you know what I'm supposed to do? I'm supposed to multiply the moles by 2 to get the moles of H positive. So it's gonna be 2.88 10 raised to the power minus 3 mole of H positive ions. Okay, so since I know that this is excess mole, okay, so I'm going to subtract excess to get the remaining moles. So it's gonna be 0.0192 minus 2 point, oh my god, 2.88 10 raised to the power minus 3. What's the answer after the subtraction? It's gonna be 0.01632 mole of OH negative ions. Okay, isn't it? Are you getting the same answer? Are you getting the same answer? Hello.
Yeah,
Okay.
sorry, my
So
mic
this
was
is
off.
the concentrate. This is the mole of OH negative ions. Now I'm going to find out the concentration of OH negative ions at the end of reaction. So the thing is that concentration of OH negative ions would be equal to mole upon total volume. Mole I got 0.01632 and the total volume is 80 plus 20. Total volume is, this is the total volume 80 plus 20. You can see 80 cm cube of NaOH and 20 cm cube of H2SO4. And then I have to convert it into the decimeter cube. So 10 raised to the power minus 3. So what's the concentration that you are getting for the OH negative ions? Of course, it's going to be 0.1632 mole per decimeter cube, right? So then after getting the concentration of OH negative ions, can apply the formula that is H positive ions into OH negative ions. I know the Kw, that is 1 exponent minus 14, and I have to find out the concentration of H positive ions, and I know the concentration of OH minus, that is 0.1632. In this way, I can have the concentration of H positive ions in mole per decimeter cube, then in the end, I can apply the relation that is going to be pH is equal to negative log of the answer. So what's the concentration of H positive ions?
Do you want me to tell you the pH? Because for the pH it's
What's the concentration of this one? As I will be putting in this formula and would get the pH. Hmm?
So it's going to be the 1 times 10 to the power of 14 divided by 0.1632, which gives
Yeah.
us 6.1275 times 10 to the power of minus 14. And then that's going to be
6.1275 10 to the power minus
times,
14, right?
yes, and that we'll put that in the log, and that gives us 13.2.
So that's the pH. Oh my God, 6 marks. Okay. Sulfurous acid is a weak acid and dissociates as shown. It forms a buffer solution when mixed with sodium hydrogen sulfate. What is mean by the term weak in this context? So weak means that what do you mean by the term weak? Yes,
Um,
that partially
it's like it
dissociates.
associates, yeah.
Yeah, partially dissociate. Partially means does not fully. What is mean by the term buffer solution? Buffer solution.
It's when it's a solution when like it resists the change in pH
Yeah,
when like
exactly.
a small amount of
The
acid
solution,
or base is added.
the solution whose pH remains constant. Whose pH remains constant. After adding after adding acid and base. Calculate the mass of sodium hydrogen sulfite, okay, that should be added to 50 centimeter cube of 0.0480 mole per decimeter cube sulfurous acid solution to form a buffer solution with pH 2.18. Ka is given to you. Ka is given to you, and they are asking to find out the mass of sodium hydrogen like sulfite. Okay, so we know that pH is equal to pKa. We know this is Henderson-Hasselbalch equation. pH is equal to pKa plus log salt upon acid. Salt upon acid. Then what should I do for this one? Yes, I know the concentration of acid. That is 0.0. Oh, 0.0480, right? And I know the pH, that is 2.18, but I don't know the pKa. So, negative log of Ka is pKa. I can find over there negative log of Ka. Ka is given, that is 1.54 exponent minus 2. So it's gonna give us pKa. What's the answer for pKa? Yep. Yes, what's the answer?
I'm not sure.
No, for this one. For this one, I'm asking. Negative log of this value to get the
Okay.
pKa.
Oh, it's 1.8125.
1.8125. And I have to find out this one. NaHO3. So what I would do in this case, uh, 2.18 minus 1.8125 is equal to log. I'm saying that this is x, right? And this is going to be 0.0480. So after subtraction, what's the answer? Yes, first. What's the answer for subtraction? Hmm? First.
1 second. 1 second. It's going to be 0.3675.
0.3675 is equal to is equal to log x and minus log 0.0480. So what's the answer for log 0.0480? Do it fast. Log into 0.0480.
Log 0.0480 would be minus 1.3187.
Minus 1.31, right? Minus 1.31, then?
Yeah. Minus 1.3188.
Okay, so it's gonna
I'm
be
rounding it off because it's a long number.
0.3675. It would be 0.3675 minus minus plus. Then again, it would be negative over there. Right. 1.3188. So it's equal to log x. What's the answer after the subtraction? Take anti-log of that value. It should be uh 0. Yeah, what's the answer?
Antilog of, I'm sorry.
Tell me the answer for this one. Why are you taking so much time in calculation?
I'm sorry, it's like my calculator isn't working, so it's kind of like taking a bit
Oh
of
my
time.
God. Okay.
Yeah. It's minus 0.9513.
512. So now you have to take anti-log of this one to get value for x. And by the way, x is this one. Concentration of, oh my God. X is NaHSO3, and it's gonna be
0.111.
0.1188 mole per decimeter cube, right?
Yeah.
So it's the concentration of uh, NaH and SO3, right? And what they were asking? Mass of sodium hydrogen sulfate. So mass would be equal to mole multiplied by mR. Mole is 0.11188. mR is given to you, that is 104.1. When you will be multiplying it, so you would be getting the mass. It's very simple. What's the answer? Uh,
It's gonna be 11.64. 11.65 actually.
11.65. No, 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 no.
Yeah.
Oh, should be added to. Oh, okay, okay. Wait. First of all, it's a mole per decimeter cube. I did a mistake over there. It's a mole per decimeter. Mole per decimeter cube means that per 1000 centimeter cube, by the way. So, and in the question they were saying should be added to this much volume. This much volume. So means that I have to find out the mole in this much volume. So I would say that if 1000 centimeter cube has this much moles, if 1000 centimeter cube has this much moles, how much moles would be there if I have 50 centimeter cube? So X would be equal to 50 multiplied by 0.11188 and divided by 1000 and divided by 1000. So you would be getting 5.5 941 exponent minus 3 mole. Now, I have to multiply this with the MR of NaHSO3, that is 104.1, to get the mass, that is going to be 0.582 grams. This is the mass of NaHSO3. Okay. Okay, now we have question number 18. This question is about carbonyl compounds such as ethanol. Ethanol reacts with the weak acid hydrogen cyanide to form uh, a racemic mixture. Complete the mechanism for this reaction include curly arrows, the structure of the intermediate, and any relevant lone pairs and dipoles. So what I would do in this reaction? I can say that. Let's say, first of all, this cyanide is going to have a lone pair of electron. Okay, so it would be having partial positive and partial negative. It would attack on this partial positive carbon, and of course, this is going to be removed just like that. Just like that. And I would say that for this one, I would be getting the intermediate that is going to be CH3, the same thing, and then carbon. Then I have the same hydrogen atom. Then I have cyanide ion attached, and this is going to be O negative, right? It has a lone pair of electron. And then this is going to be, it would attack on this hydrogen, partial positive hydrogen, partial negative cyanide, and this is going to be removed like that, okay? And as a result of this, this is going to be produced. That's the final answer. It's a very easy, I think so. Just we need to do this one. That's it. Explain why a small amount of sodium hydroxide solution is added to the reaction mixture by considering the nature of the attacking species in the slow step. Since you know that the why they are saying why a small amount of sodium hydroxide solution. They are saying small amount of sodium hydroxide solution is also added to the reaction mixture. Complete the mechanism. Why? Why sodium hydroxide solution is added? What do you think? Why this is added? What's the role of this sodium hydroxide in this question, in this reaction? Yes.
So can you repeat the question? Your voice is breaking.
They are saying why solution of sodium hydroxide is added to the reaction mixture. Why? What do you think? Why
Um,
this is going to be added?
to increase the concentration of the cyanide ions.
Exactly, because cyanide is acting as a nucleophile. Cyanide is acting as a nucleophile. So the thing is that OH minus from NaOH reacts with HCN to give to give a cyanide ion. So there would be more concentration of cyanide like ions. Okay. Okay.